Hi, everybody. Welcome to another session of our reading group. I should share the link in the chat as usual, and I will also share my screen. And there we go. So we can jump right into it, and then uh, as people join in, I will update the reading order. So, Artem, why don't you start?
So we now turn our attention to Hamiltonian mechanics and try to understand exactly what kind of systems it focuses on.
Wait,
We'll find
your audio is a little bit garbled. I don't know if it's just me, but
let me find a quick start on something.
was it just me or it was garbled for everybody?
Yeah, it was kind of faint for me as well.
Okay. So, Rudra, why don't you go?
Okay, yeah. We can now turn our attention to Hamiltonian mechanics and try to understand exactly what types of systems it focuses on. We will find 12 equivalent formulations of Hamiltonian mechanics that link ideas from vector calculus, differential geometry, statistical mechanics, thermodynamics, information theory, and plane statistics. The overall result is that Hamiltonian mechanics focuses on systems that are assumed to be deterministic and reversible. We will see how the physical significance of that assumption differs from mathematically naive characterizations.
Okay.
Should I continue or?
If there are no questions, yeah, please go ahead.
Okay. Mathematical characterizations. To simplify our discussion, we will first concentrate on a single degree of freedom. The first characterization of Hamiltonian mechanics is naturally in terms of the equations. Total time derivative of q equals partial p of h. Total time derivative of p is negative partial q of h. We will want to treat phase space as a generic two-dimensional space, i.e. manifold, like we would for a plane in physical space. We will reserve the term coordinate for the position variable q, while we will refer to the collection of position and momentum as state variables. And we will note them as psi a equals q comma p. We will now define the displacement field. SA is the time derivative of psi a, which is the time derivative of each of the components individually, which is a vector field that defines the evolution of the system in time. Hamilton's equations then can be expressed as SQ equals partial P of H, SP equals negative partial Q of H. To bring out the geometric
Wait.
yeah,
Stop
that's
here.
sorry. Yeah, sorry.
So the thing that is important to me is that again, free space for us is just right now is just a manifold, and so if you are more mathematically inclined, people will try to say that this is the cotangent bundle, and for us it's not. It's just a manifold because there are phase spaces that are not cotangent bundles. They don't have that structure. And then the other thing that we want to be able to do in our head is to use different coordinates that are neither position nor momentum, just a complete mixture of the two. So there is no sense that you have to chart the states with position and momentum. In fact, you can chart them with position and velocity, and the fact that you're charting the states with position and velocity doesn't mean that you change the structure. It's just you're just using different coordinates in the same way that you would use a polar coordinate or Cartesian coordinate in space. There's nothing else. And then to avoid the confusion between the generic term coordinate that you have in math, when we talk about coordinates, we will refer really to the positions, to the cues. And when we'll talk about the state variables, then it's the whole thing. Like in principle, phase space itself is a manifold, so position and momentums mathematically are the coordinates of the state space manifold. But then if you use coordinates for everything, you don't understand anything anymore. So coordinates for us are gonna be the ones that are basically defined by a frame, and then state variables are gonna be these generalized that are indexed with this. They're noted with this xi, and then let's say the index is something that span Q and P in this case. Okay. Okay, so Robbie.
To bring out the geometric meaning of the equations, we introduced the matrix omega sub AB. I'm not. Should I read each entry in the matrix?
No, it's fine. Just leave it. So for me, it's just a note that again, these are all the possible permutation of the indexes, and again, the fact that we're writing them down is important.
Which rotates a vector by a right angle. And then there's a footnote. The notion of angle is technically ill-defined in phase space, but this slight imprecision makes it easier to get the point across. That is, if VA equals VQ VP, then VA equals VB omega BA equals minus VP VQ. We can rewrite equation HM1D as
both, yeah.
I don't know if you want to say anything about that, or should I continue?
I'll say later. Finish the paragraph, and then I will go through the whole thing.
And we have footnote 14 as well. The notation is purposely similar to how indexes are raised and lowered in general relativity. Shouldn't that be indices?
It's you can say both, I think.
Okay. How indexes are raised and lowered in general relativity by the metric tensor. Since omega AB plays a similar geometric role in phase space. One should be careful, however, that omega AB is antisymmetric. Omega AB equals minus omega BA. So it matters which side is contracted. In terms of symplectic geometry, the rotated displacement field SA corresponds to the interior product of the displacement field with the symplectic form, usually noted as I
have no idea how to read that, but that's the notation that you have in symplectic geometry.
Yeah, I'm sorry. There's some beeping going on my end. So I'll continue at the right below equation HMG, which tells us that the displacement field is the gradient of the Hamiltonian rotated by a right angle. Note that the gradient is perpendicular to the lines at constant energy. Therefore, as we can see in figure 1.6, a right angle rotation gives us a vector field tangent to those lines, making it geometrically evident that the value of the Hamiltonian is a constant of motion. Condition HMG is just a re-expression of HM1D, though it is already useful. We want to find different mathematical conditions which turn out to be equivalent to the equations.
Okay, is there anything unclear in this? Okay, maybe somebody should read the figure because it basically shows like pictorial what's happening.
Okay, it's my turn. So
maybe I'm gonna do it. The surface plot shows the value of the Hamiltonian for a harmonic oscillator, h p squared over 2m plus 1/2 k q squared. Red means higher value. The lines are the regions at constant energy h. On the left, the gradient of the Hamiltonian is shown. On the right, the displacement field is shown, which is the gradient rotated by a right angle. Note how the displacement is always parallel to the lines at constant energy.
Okay, so again, this idea of the rotation is a little bit ill-defined because there is no such thing as an angle between position and momentum, right? I mean, we could stretch this up however we want. It would still be a fair representation, so then the rotation wouldn't be 90 degrees. But basically, what we're meaning is that we're switching the components from one side to the other and putting a minus sign. So anything that sort of was in the direction of the increase of the energy becomes a direction of constant energy. That's what's happening. And the other bit that was there in the footnote, so what we're trying to do by writing expression like this, we're trying essentially to find a version of Einstein's index notation and summation notation that works in phase space, such that we can bring the physical idea more closer to, like the notation closer to the things that we want to say in physics. If you do GR, you typically use this type of notation. You can also use the index-free notation, but the typical physicists prefer this just because it allows them to interpret better what's going on. And what we found is that doing something like that for phase space itself as well allows you to get a better intuition. So that's basically what we're doing. Everything that we're doing here can be re-expressed in the standard mathematical way, but I just don't do it because most physicists wouldn't know it anyway. So, okay, next.
Right. We start by noting that the displacement field as expressed by 1.37 looks very similar to a curl of H, except that it is a two-dimensional version. In vector calculus, a vector field is a curl of another field if and only if its divergence is 0. Footnote 15. We will leave for now topological requirements as they will be a distraction from the overall point. This holds here as well. First, we can verify that, and there's this equation, 1.38.
So this is kind of where this would be a divergence in 3 dimension. You're taking the derivative of every component along that component and then summing them, right? So this is how you would write it in a compact form. Then you expand it by simply expanding the vector, expanding the sum. And then you use Hamilton's equation. You note that the partial derivative commutes, and then you have a 0.
Right. Geometrically, this means that the flow of SA through a closed region is always 0, as shown in figure 1.7. That is the closed loop integral of SA dp minus SP dq is equal to 0. Note that since we are in two-dimensional space, a hypersurface has dimension n minus 1 equals 2 minus 1 equals 1, and therefore hypersurfaces are lines. Therefore, we have this, which is the same loop integral, but then you use Hamilton's equations to show that it leads to, 0.
Right. So what we're doing here is again, we're doing the flow, and then we are taking so the flow has to be perpendicular, right? So we kind of have like a two-dimensional version of the vector product between the flow and the line. And then again, you do the same substitution with the displacement field with Hamilton's equation, and then you find that what this is just the differential of the Hamiltonian, which over a closed loop is going to be 0 because you're starting at a point, and so you're doing h at that point minus h at that point, and it's simply 0.
And this combination of SQ minus SPdq, that is the curl.
No, it's like the vector product. So you know when you have when you're calculating the flow of a field through a surface, you have the vector product between the surface element and the vector field, right? Because you're looking at something that is perpendicular,
And
right?
in this case, it's just the omega defines the inner product, and this is where the minus comes from.
Right. That's what we see later, that basically this is the same thing, that's what the omega doing. This rotation by 90 degrees is basically saying, instead of making a scalar product, I'm gonna make a product with something and the perpendicular.
Yeah, okay.
Okay, is my mic alive now?
Yes.
Do you hear
Yes.
me?
Yes.
Okay,
Now it's
great.
good.
Okay, so that, yeah, or did I? That's probably part of the last part, but since I'm already starting, okay, that is the flow of the displacement field is the line integral of the gradient of the Hamiltonian, which is 0 over a closed curve, as we've said. Conversely, we can see that each divergenceless field in 2 dimensions admits a stream function h that satisfies
Wait a
HM1D.
second. Let's read the footnote of the figures, because it again explains better what's happening in the geometry.
Okay, so we have figure 1.7. The flow of the displacement field SA through a path shown on the left is equation to the difference of the Hamiltonian at 2 points, and you can read that. The net flow of states through a region, i.e. the flow of the displacement field through the boundary, is 0, as shown on the left. This means that SA is divergenceless and will admit a stream function, a potential which corresponds to the Hamiltonian H.
Yeah, I think that the ease equation should have been ease equivalent.
Yeah.
Okay.
Okay.
Okay. If there are no questions, you can go ahead, read where you were reading.
Okay, so yeah, I was saying that this field admits a
Yeah,
stream
conversely.
function. Yeah, conversely, we can see that each divergenceless field in 2 dimensions admits a stream function h that satisfies HM1D. Geometrically, we can construct H in the following way. Take a reference state O in phase space and assign H of O equals 0. For any other state P, consider the flow of S through any 2 lines that connect O and P. Given that the flow through the region contoured by those lines must be 0, the flow through each line must be equal. Therefore, the flow through a line that connects O and P only depends on the states. It is path independent. We can assign H of P to this integral. And if we expand the differential of H, we have, using the product rule or
Yeah, chain rule.
chain rule, yeah. Right. And there we use Hamilton's equations to
No, here you find Hamilton's equation.
Let me see.
So the idea is
Right,
that
we input the stream function that we have above, and we obtain HM1D. Right, so if we equate the components, we recover HM1D. Geometrically, at least for the one-dimensional case, we can understand the difference of the Hamiltonian between 2 states as the flow of the displacement field between them. Okay.
Okay, so we're trying to re-understand the Hamiltonian itself at this point, not as energy, but just as the geometrical property of flows in essentially surfaces that connect paths that connects the states.
We conclude that the following condition, the displacement field is divergenceless, partial A SA equals 0 is equivalent to HM1D. Unlike HMG, this is truly different. This is a truly different mathematical condition. Should I continue?
Yeah, so
Because
you
it
should
was a
continue. It was just, yes,
okay.
that's so short.
Having looked at the flow through a region, we turn our attention to how regions themselves are transported by the evolution. Liouville's theorem states that volumes of phase space are preserved during Hamiltonian evolution, which in our case will be areas over the QP plane. To see this, let us review how variables transform together with infinitesimal volumes.
Okay, so this is a Courant transformation from xi to xi hat. And then the differential of xi hat are just the differential of xi with the partial derivative. This is just the Jacobian of the transformation. And the volume is the product of all the differentials, and it transforms with the determinant of the Jacobian. So the determinant of the Jacobian essentially tells you how volumes are going to be change if they are stretched or shrunk. And this is why, if you want something to be transformation to be nice, you want that determinant to not be zero, because otherwise it's like you're taking volumes and squishing them to something that is lower dimension, and then you can't be invertible, right? So that's sort of a condition. And so in our case, then it's just the product of the differential in new coordinates is the product of differential of the old coordinate times the Jacobian. Robbie?
This tells us that mathematically, a transformation is volume preserving if the determinant of the Jacobian is unitary. If Q and P represent the evolution of Q, or if Q hat and P hat represent the evolution of Q and P after an infinitesimal time step, delta t, we have.
Okay, so this is the new position, which is the old position plus this would be a dq, and then for the since it's a transformation in time, it's going to be dq dt times the variation of t. Same thing for p, right? So this is the first order variation for q, and then what you do is just take this expression and put them inside the Jacobian in the formula, right? And so if you derive this this would be q hat, the expression of q hat derived by q, you basically have 1, because dq is equal to 1, and here you have the partial derivative of sq by q. Same thing here, you're going to the derivative in p. This is a constant because it's a derivation of constant q, and then you have derivative of sq with respect to p, and basically you have everything else. Then what you do is calculate the Jacobian, this is the determinant, and the determinant is just the product of the diagonal minus the diagonal of the cross terms. And if you do the calculation, you're going to have just one leading term that it's 1, so 1 times 1. And then you have the first order term, which is this multiplied by this, and this multiplied by this. So you essentially have partial QSQ plus partial PSP, which you should recognize. Robbie, continue.
Note that the first order term is proportional to the divergence of the displacement field. Therefore, the Jacobian determinant is equal to 1 if and only if the displacement is divergent to this. In other words, condition the Jacobian of time evolution is unitary, and condition volumes are conserved through the evolution are equivalent to what is that? dr div. Yeah. We have found a third and fourth way to characterize Hamiltonian evolution. And I'll pass it off to Tobias.
Yep. Okay, while condition dr volume is expressed in terms of areas, similar considerations will work for densities because a density is a quantity divided by an infinitesimal area. In fact, densities, where we have the transformed density, which is also multiplied by the Jacobian, transform in an equal and opposite way with respect to areas, i.e., the Jacobian determinant is on the other side of the equality. The unitarity of the Jacobian determinant then is equivalent to requiring that the density at an initial state is always equal to the density at the corresponding final state. Both areas and densities are transported unchanged by Hamiltonian evolution as shown in figure 1.8. Therefore, densities are conserved through the evolution is yet another equivalent characterization. And there we have figure 1.8. Should I read it maybe?
Sure, go ahead.
So on the left side, we see how the displacement field is a transports area of phase space to equal areas of phase space. It's basically just taking the same area. On the right, we see Hamiltonian evolution transports a probability distribution point by point. The value of the probability density remains the same as it moves over phase space.
Right. To get a yet different perspective, we can reframe these arguments in terms of omega AB and SA. Given two vectors VA and WA, area of the parallelogram they form is BQWP minus BPWQ. Yeah, sure. This can be rewritten as VA omega AV WB, which means we can think of omega AB as a tensor that, given two vectors, returns the area of the parallelogram they form. Footnote 16. More properly, omega AB is a two-form. If we denote V hat A as partial V psi hat A BV, and also for transformation omega hat, W hat A, the transform vectors, the invariance of the area can be written in the following form. So it's just applying the two form in both cases. Equation 1.44, and then since, and here you're just writing out omega. No, let's see.
Okay, so this is what happens here is you're doing the usual trick where you can say I'm transforming the vectors and then using the form that I had before, or I can take the Jacobian out of the vectors and put them in the form, and now you are transforming the form and keeping the vectors the same. So in this case, you're basically have the future vectors, and you ask what is the area, given the future vectors, what is the area, right? Because this is telling you what is the area essentially right now. Here, instead, you're asking what is the area of the future. So I give you the present vectors, what is the area that these vectors are going to have in the future? And then, of course, you want these two to be the same.
Okay. The previous equivalence means that omega AB is equal to omega hat AB. That is, omega AB remains unchanged through this transformation. In other words, preserving the area for all possible pairs of vectors is the same as preserving the tensor omega AB that returns the areas. We now see that omega AB plays such an important geometric role that the evolution leaves omega AB invariant, and this is DI simp. Is yet another equivalent characterization of Hamiltonian mechanics.
Okay, it is useful. Give me a second. It is useful to look more closely at the definition of the Poisson bracket. And we can look at that. And for a single...
Let me go through that. I don't know how many of you have seen the Poisson bracket, but this is how it's defined. It's you basically have two function of Q and P, in this case, F and G, and you do the partial derivative of F and G first with Q and P, and then a minus, and then you invert either the P and Q or the F and G, like depending on how you prefer. Here I'm keeping F and G the same, but you said you can see that the P and the Q are different. Like this is how you study it, and that's it. What we are showing here is that this expression, the Poisson bracket, is actually the Jacobian determinant, right? Because this is the F and G with the partial derivatives, as if you were making a coordinate transformation from QP to FG. And then you can see that that this product of the two is this part, and the product of the cross terms is this part. So of course, if you haven't seen the Poisson bracket, this is going to be meaningless to you. But
by the way, like a very minor pedantic nitpick, but since we're not using the full unitarity of the matrix, maybe we should just say that it's orthogonal, since that's what we get. I mean, in this context, I mean, orthogonal is unitary, but
orthogonal. What is orthogonal here?
I mean, like a matrix was determinant one. Like for unitary matrices, we can have whatever determinant was whatever complex determinant was magnitude one, I believe. So like
And so this, in principle, is not gonna have
no, I
determinant
mean,
one.
before that, when we said that the Jacobian has to be unitary, it's
So here.
I mean, if we are pedantic, it's not just unitary, it's orthogonal. But I don't know if that basically adds nothing to this, but we can
Okay, I'm
be
not
more
understanding,
precise.
so sorry.
No, I mean that when the determinant is one, matrix is orthogonal, I believe, and like unitary matrices we can have.
So that there is, if you're referring to the orthogonal group, yes, orthogonal groups have a unitary Jacobian. I don't recall, are all the matrix with unitary Jacobian part of the orthogonal group? I don't remember the definition.
I'm just trying to say that unitary matrices are like a broader context than matrices was determinant one, and I believe like the name for matrices with determinant one would be orthogonal matrices. Somebody can correct me here if I'm
Okay,
wrong.
I'll check.
We are
I'll check.
correct that the Jacobian is unitary. That's correct, but we can be like a bit more precise.
Yeah,
Since
since we're working explicitly in real coordinates, we're working in this case in R2.
Yeah.
So
Yeah, that's the same pretty much.
orthogonal, yeah, is the same as unitary.
Yeah.
But yeah, so
Okay, but it's not the same when you're in complex space, I guess that's the idea.
Yeah. But
yeah, because orthogonality doesn't really make sense because you need a complex conjugate to define the inner product on the complex space.
Okay.
Yeah, that's why I'm saying it's really like minor and pedantic. Like
Okay.
everybody understands what we mean here.
Okay.
Okay, so let's where were we? So yeah, we have the definition of the Poisson bracket, and for a single degree of freedom, the Poisson bracket coincides with the Jacobian determinant, where f and g are the two new variables. It essentially tells us how the volume changes if we change state variables from QP to f and g. Canonical transformations then are those that do not change the units of area. The Poisson bracket can be expressed, and footnote 17 is to see how our definitions and notation map to those that used in differential geometry. Let us define partial A of H as omega AB partial A of H. I'm not reading upper and lower indices, but you can see them.
Yeah,
Note
so
that
there is a mistake that I have to fix, but go ahead. It's the partial on the right side should be partial B because you're contracting
yeah,
the B's and leaving the A
right.
free. So
Right. Note that partial A of H corresponds to the Hamiltonian vector field of H. Usually noted X sub H. The Poisson bracket is usually defined as omega of X sub F and X sub G. In our notation, this becomes, I'm not going to read that.
yeah, so the point is that we are doing a similar symbol manipulation that you would do again when you are in curved space in GR, where you have the sort of the partial up and the partial down as two different types of derivatives, and you get back the Poisson bracket just by doing the simple symbol manipulation. And if you would do that in the standard notation of what people typically use in symplectic geometry, you have to remember, like, there are a bunch of different steps in between, and you have to remember more relationships. Instead, here you basically just have to remember one, and everything sort of works much nicer. That's basically it.
Yeah, and one can see how the notation mimics the Einstein notation of general relativity and avoids the introduction of ad hoc symbols.
Yeah.
Okay, so, and here, the Poisson bracket can be expressed as, okay, what are we doing here?
So this is basically what was, recalculated here.
Okay.
Yeah, instead of writing it like this, you use the omega again to calculate this 2 by 2 determinant. And the only thing that you have to be careful is that you're going to get this minus sign, which you can also include into by switching the indices of A and B because it's antisymmetric. So like if you write it like this, then G has to become first, and you contract it on one side, and F becomes second.
Okay, and where again, we have omega AB defined here, and it's the inverse of the one with lower indices.
Yeah.
The invariance of the Poisson brackets is equivalent to the invariance of the inverse of omega with lower indices, which is equivalent to di simp. Therefore, the evolution leaves the Poisson brackets invariant is yet another equivalent characterization. So again, we see how omega AB plays a fundamental geometrical role.
We can also rewrite the flow of the displacement field, equation 1.49, as the line integral of the rotated displacement field SA. We can do that because in 2 dimensions, the flow through a boundary is effectively a line integral along the boundary with the field rotated 90 degrees. This means that the following condition, the rotated displacement field is curl-free, partial A as B minus partial B as A equals 0, is equivalent to condition dr div, and the footnote there says, those familiar with relativistic electromagnetism will recognize the expression partial A as B minus partial B as A as the generalization of the curl. More precisely, it is the exterior derivative applied to a one form. In fact, we can read equation HMG as saying that the rotated displacement field is the gradient of the scalar potential H.
Right. So if we go back, oh, I have links. I can click the links. If you go back here, there you go. So we have that the rotated displacement field is just the gradient of H. Or if it's the gradient of H, then it means that the curl of SA is 0 and vice versa, which is what we have here. We have here.
Okay. We can see that we have found plenty of alternative characterizations of Hamilton's equations, HM1D or HMG. Following conditions relate more directly to the displacement field SA, while the conditions simp, poi, and curl relate more directly to omega AB and the rotated displacement field S sub A. Nonetheless, they are all in terms of the mathematical description. While these are useful, the final goal of reverse physics is to find physical assumptions, not just equivalent mathematical definitions. So it is time to step back and try to understand what the math is really about.
Okay, I would stop here for for some time, so to see if there are any questions. I mean, this throws a lot of stuff on the plate, but that's kind of the point. Okay. Okay, so clear enough. We just continue then.
Okay.
Tobias? Yeah.
The physical characterizations. Let us first reflect on what we just found out. The defining characteristic of Hamiltonian mechanics is not the transport of points, but the transport of areas and densities. If classical Hamiltonian mechanics were really about and only about point particles, there would be no reason for it to be characterized by divergence-free volume preservation of densities. In fact, there would be no reason for the equations of motion to be differentiable. Differentiable equations are exactly needed if we need to define the Jacobian, the transport of areas, or of densities defined on those areas. Classical point particles, then, are more aptly conceived not as points, but as infinitesimal regions of phase space, as distributions so peaked that only the mean value is important.
Finish the thought.
Okay. This, in retrospect, matches how classical mechanics is used in practice. Planets, cannonballs, pendulums, beads on a wire, all the objects we study with classical mechanics are not point-like objects. They can be considered point-like if their size is negligible compared to the scale of the problem. If the distance between two celestial bodies is smaller than the sum of their radii, the point particle approximation clearly fails. This is also consistent fluid dynamics and continuum mechanics, where we are literally studying the motion of infinitesimal parts of a material. It is interesting to see echoes of these considerations present in the mathematics. And footnote, we will want to investigate this link in more detail later. We'll go on even more?
No, Alina, well, let's go. Let's go.
Yeah.
Okay. If we look at physics more broadly, we realize in statistical mechanics, we already have physical interpretation for volumes of regions in phase space. They represent the number of states. Hamiltonian mechanics then maps regions while preserving the number of states. This means that for each initial state, there is one and only one final state, which leads to the following condition. The evolution is deterministic and reversible, DREV. Note that by a reversible here we mean that given the final state, we can reconstruct the initial state. Given that areas measure the number of states, drEV is equivalent to drvol, which means this is another characterization of Hamiltonian mechanics. You can also see a connection to the conservation of densities. We assign a density to an initial state, and we claim that all and only the elements that start in that initial state will end in a particular final state. We'll expect the density of the corresponding final state to match. That is, if the evolution is deterministic and reversible, it may shuffle around a distribution, but it will never be able to spread it or concentrate it.
This makes us understand at a conceptual level why a dissipative system like a particle under linear drag is not a Hamiltonian system. A dissipative system will have an attractor, a point or a region to which the system will tend given enough time. This means that in time, the area around the attractor must shrink, the density will concentrate over the attractor, but this is exactly what Hamiltonian systems cannot do. Therefore, Hamiltonian systems cannot have attractors, they cannot be dissipative. By the same argument, they can't have unstable points or regions from which the system always goes away.
Yeah, continue.
What may be confusing is that the motion of a particle under linear drag may seem reversible, in the sense that we are able to, given the final position and momentum, reconstruct the initial values. Mathematically, it maps points one-to-one and would seem to satisfy drEV, even though it is not a Hamiltonian system. This is a perfect example of how focusing on just the points leads to the wrong physical intuition. Physically, we would say that a 1 meter range of position allows for more configurations than a 1 centimeter range, even though mathematically they have the same number of points. If we understand that states are infinitesimal areas of space, we can see that a dissipative system, though it does map the center points of infinitesimal areas one-to-one, it does not map the full infinitesimal area one-to-one. In this sense, dissipative systems fail to be reversible.
Let that sink in. We have found that if the system is deterministic and reversible, it admits a Hamiltonian, a notion of energy, and that energy is conserved over time. This may seem like a surprising and unexpected result. In retrospect, we can make an argument for it based on familiar physics considerations. If a system is deterministic and reversible, it means that its evolution only depends on the state of the system itself. This means that it does not depend on the state of anything else. A system whose evolution does not depend on anything else is an isolated system. Therefore, a deterministic and reversible system is isolated. And from thermodynamics, we know that an isolated system conserves energy. It should not be surprising, then, that a deterministic and reversible system conserves energy. However, we found that not only does it conserve energy, it defines it. Therefore, this link between mechanics and thermodynamics is actually deeper than we may think at first, and we should explore it further.
The idea that a dissipative system is not reversible sounds true on thermodynamic grounds. But thermodynamic reversibility is not the ability to reconstruct the initial state, but rather the existence of a process that can undo the change. Alternatively, a process is thermodynamically reversible if it conserves thermodynamic entropy, which is a more precise characterization. In footnote 20, the actual existence of a reverse process is not something that can always be guaranteed. We should not then confuse the two notions of reversibility, but we can easily show their relationship. The fundamental postulate of statistical mechanics tells us that the thermodynamic entropy, S equals kb log W, is the logarithm of the count of states, which corresponds to volume in phase space. Since the logarithm is a bijective function, conservation of areas of phase space is equivalent to conservation of entropy. Therefore, the evolution is deterministic and thermodynamically reversible, is yet another characterization of Hamiltonian mechanics.
So hopefully there is nothing too weird about all this. Tobias, I think, is up.
There is another type of entropy that is also fundamental in both statistical mechanics and information theory, the Gibbs-Shannon entropy, which is given a distribution rho in integral over rho log rho for phase space minus rho log rho, which is defined for each distribution. Recalling the transformation rules for both volumes and densities, we have that from the original definition, we get two Jacobians. Then you use one of them to redefine your integration variables. And then we expand the log, right? No,
Yeah.
we don't expand. It's like product rule.
Product rule of the log. Yeah.
So we get the original term just in the new coordinates that gives us the entropy of the transformed state, and then the extra term is just the has the Jacobian and the logarithm. If the Jacobian is 1, then the log is 0, and this term disappears, I guess. Okay, so information entropy then remains constant if and only if the logarithm of the Jacobian determinant is 0, which means the Jacobian determinant is 1. Therefore, the evolution conserves information entropy is equivalent to that the Jacobian is 0, and this is yet another characterization of Hamiltonian mechanics.
Yeah, the Jacobian is 1, not 0.
Yeah.
So you might have noticed by now that all these conditions, dr, it's basically the class of equivalence, and then the other letters are the type of expression in that type of equivalence condition. Alina?
Yeah, the fact that determinism and reversibility is equivalent to conservation of information entropy should not be, in retrospect, surprising. Given a distribution, its information entropy quantifies the average amount of information needed to specify a particular element chosen according to that distribution. If the evolution is deterministic and reversible, given the initial state is equivalent to giving the final state, giving the initial state is equivalent to giving the final state, and therefore the information to describe one or the other must be the same. Determinism and reversibility then can be understood as the informational equivalence between past and future descriptions. Lastly, given the entropy is often associated with uncertainty, it may be useful to understand how Hamiltonian evolution affects uncertainty. Given a multivariate distribution, the uncertainty is characterized by the covariance matrix. They're defined. The determinant of the covariance matrix gives us a coordinate-independent quantity to characterize the uncertainty. If the distribution is narrow enough, we can use the linearized transformation to see how the uncertainty evolves after an infinitesimal time step delta t. We have, and here you have the determinant of the covariance matrix.
So this is the covariance matrix in the new coordinate.
Right.
And then since it's just a linear object, it will be transformed by applying the Jacobian essentially on both sides. And since now you are interested in the determinant of the products is the product of the determinants, and so you get the final expression.
Right, so you get the same determinant, which means the uncertainty remains unchanged if and only if the Jacobian is unitary. So the evolution conserves the uncertainty of big distributions, is equivalent to the Jacobian unitarity, and is another characterization of Hamiltonian mechanics.
Artem?
Okay, so this connection gives us yet another insight on the nature of determinism and reversibility in physics. Given that all physically meaningful descriptions are finite precision, A system is deterministic and reversible in a physically meaningful sense if and only if the past or future descriptions can be reconstructed or predicted at the same level of precision. This gives us another perspective as to why areas and densities must be conserved.
Rudra?
Assumption of determinism and reversibility. We have found 12 equivalent characterizations that link Hamiltonian mechanics, vector calculus, differential geometry, statistical mechanics, thermodynamics, information theory, and plane statistics. Though we only talked about the case of a single degree of freedom, it gives us a much better idea of what systems Hamiltonian mechanics is supposed to describe. Those that satisfy the following. Assumption DR, determinism and reversibility. The system undergoes deterministic and reversible evolution. That is, specifying the state of the system at a particular time is equivalent to specifying the state at a future determinism or past reversibility time.
You can finish.
We can see how this concept is implemented mathematically. It is not simply a one-to-one map between points. Classical particles should be more properly thought of as infinitesimal regions of phase space. Conceptually, the counter states, thermodynamic entropy and information entropy are all conserved, and are all equivalent characterizations of determinism and reversibility. In terms of physical measurement, past and future states are given at the same level of uncertainty. But the most important lesson is that the foundations of classical mechanics are not disconnected from the foundations of all other disciplines we encountered. A full understanding of classical mechanics means understanding those connections as well.
So question on the chat. Can a system be deterministic and reversible and not be a Hamiltonian if we take a particle under drag and keep track of how much kinetic energy momentum is lost, then the information is still there. So that's kind of the point. The information is being degraded in the sense that it's going to be harder and harder to get that information. And at some point, for example, you're going to have noise, and then at some point you lose that information to the noise. So really in a strict sense, you need this conservation of information, conservation of mapping things one to one. And then conceptually, again, if something is truly deterministic and reversible, it means that the system itself only the change in the system itself is only determined by the system itself, right? So if you now have something like friction that it's taking energy out, clearly the motion of that system is not fully defined by the state of the system anymore. You need something else. Something else in the world is gonna change, and then you need to keep track of that system as well if you want to have a closed system. So basically, no. Like you can look at it, and this is the beauty of reverse physics. You can look at the argument in so many different ways that then you always have a failure in any other perspective. And again, it's a definition of what we mean by deterministic and reversible. What you would have in a particle undergrad would be something like predictable and retrodictable. So you are able to make the map to the point, but you are not you don't really have determinism and reversibility in the physical sense. Any other questions? We did the hour perfectly this time. Also, is it intuitive why we have divergence-less condition and not a continuity equation? What do you mean by continuity equation in that sense? maybe in extended phase space. So we're going to have extended phase space much later, and we will see that basically all the things that we're saying are going to be true for the extended phase space as well. And by the way, whoever sees this video in the future, if people want to join, please send me an email, and you can be added in the group and on our Discord server. So while Julius types in the chat, are there any questions from anybody in the Zoom call?
I think he was talking, I guess, about continuity equation as in like fluid dynamic sense. Right? Which is very similar.
Okay.
So the same, just expressed in a different way.
Right. So the continuity equation in that sense would just be the divergence-less, because you should think it as a flow without sinks or sources. So in the continuity equation, you have your divergence of the field, and then it's equal to some source or sink term, and it's like you don't have that source or sink term. So in fact, one of the things that we're kind of futzing around with one of a professor is trying to understand whether we can put in the framework that we have these sinks and source terms in a way that then we can also use the other interpretation that we have for what's it called, for the action principle, so that we can sort of have an action principle for things that are dissipative or driven. But yeah, so that's okay. So yes, that's basically it. It's what we have is exactly the continuity equation. Is just that the source and sink terms are zero. At least in the two, 1 degree of freedom. Then in multiple degree of freedom, we'll see next time that things become a little bit more sophisticated, but the essence is still the same. And thanks, Tobias, for clarifying the question. Any other questions?
So
Okay.
what you said about adding a source term, would that also change the topology? Because we had that if and only if the divergence is 0, then you can express it as a curl, but that thing would change.
So,
Is that
so it does not change the topology. So there is the issue of the topology. There is, for people that don't know, is that you can go from essentially something divergence-less to potentials only if you have a contractible region. So if you have something like a donut, you start having problems. So that is a question of whether we can have a state space that it looks like a donut. So that's something that I don't have an example of a symplectic space that we use in physics that has these properties, that it's not contractible. It doesn't mean that there aren't people in physics actually using them. It's just that I'm not aware of one. And so that would be the first question, like do we have an example? And that would be interesting. And then the second question is that if there are no examples, can we make an argument of why that should be the case? And quite frankly, I don't know either case. Now, when you have source and sinks, the source and sinks are still on, let's say, on the region, and so the topology is still the same. It's just that you have essentially. If you imagine that there is a flow, right, there are some regions that sort of contribute to the net presence of the flow, and some that make the flow disappear. And so the topology is still the same. What you're going to lose is that, again, you don't have this preservations of volumes, and in the multiple degrees of freedom, things can become even more complex. And so we're trying to understand exactly where those essentially more freedom for the flow, whether these things can also be expressed as some type of potential in the same way that the Hamiltonian is sort of the potential for the deterministic and reversible flow.
okay?
And there mathematically what happens, we're going to see later that you can make this potential because the form is closed, that omega is a closed form, and that's why we can have a potential. And so when you are dissipative or driven, then that form is not closed anymore. So you can't just say that it's the exterior derivative of a lower form. But there is this what is it? DRAM cohomology, and there is a
DRAM cohomology.
Yeah, and then there is a DRAM decomposition, so that you not only have an exterior derivative, but you can also have the co-differential. And so we are trying to see whether the sort of the dissipative part can be put in the co-differential and see if we can make the thing to work. And we were futzing around with the math right there. So that's more or less, yeah.
Interesting.
So Julius, again from the chat, talking about donuts, and what about particles constrained only on a surface? Is the number of states concerned with the motion and the constraint? So the constraints are on the space. So the donut is on the position side. And then when you create things with the momentum side, right, you start having a different thing. So I do not know exactly how the topology of one relates to the topology of the other. And again, other people might know. But states are conserved. If you have a Hamiltonian motion on a donut, you're still going to conserve the number of states. Everything works exactly as we did. So while it may not be true that you can have sort of let's say a global potential, right? Something that you can express in all coordinate. You always have it locally, and then you can sort of whenever you have patches on the patches, those potential have to agree, and so then you could basically cover the whole thing in patches, and it still works. And so at that point, the potential is just the fact that you're able to make all these patches and look at things. Okay, so we stop it here. Thank you
I
guys
have one
for
more thing.
joining. Oh,
Sorry.
there you go.
Talking about the continuity equation. The continuity equation involves some kind of distribution or like a density of a fluid, but we can also see it as like a probability distribution. If we evolve these, the closest analogy would be like evolving a distribution with a Poisson bracket, right? The total derivative of the probability density is something like the Poisson bracket, right? With the
Correct. So
Hamiltonian.
when you have a distribution in actually, when you have any function of position momentum you want to evolve in time, the total derivative of, in this case, of the distribution is going to be the Poisson bracket between the distribution and the Hamiltonian.
Yeah, and that will be the term that in a continuity equation is like the divergence of the velocity field or something like that, right?
Yes, it's the divergence of that product with the distribution itself. It should be.
Yeah, so I think basically that the Poisson bracket is conserved or something like that could be connected. I'm not sure, but like if you want to like see it as close as possible to continuity equation, you should look at the Poisson bracket.
Right, and I think at that point, if you had the source term, you would basically have an extra addition to the Poisson bracket for the source and sinks. Like the source and sink term would be an addition to the change.
Yeah, I think so.
I mean, regarding donuts, I'm not sure if we have space. Like I'm not aware of situations in physics when the phase space is a donut, but like when configuration space is a donut, we like it happens all the time when you impose like periodic boundary conditions. So
yeah. Mhm.
But like for phase space, what would that be? That would be like if you have a huge positive momentum, you wrap around to negative momentums. Yeah, that's.
I have no idea. Yes. So if you have okay, so there is an example that I can give. So if you have if you're studying angular momentum, right? Then the phase space is just the positions, and the conjugate variables are the angular momentum in the vertical direction, for example, and the angle, right? Those would be the two conjugate variables. So in that sense, that space, since it's a ball, it's not contractible. Well, it's not a donut, but it's a ball. But it's a very specific case, and I mean the failure there is minor because you take 1 point away, and you can define everything. So you don't have that much of a problem. You can actually write the Hamiltonian, because the Hamiltonian is going to be just a function of the angular momentum in the direction of the magnetic field. So you don't even need the angle, and so you can actually write it without a problem, even though you are in a space that it's not contractible. So again, there is an example where the space is not contractible, but it's absolutely not interesting. I don't know if there are, with angular momenta, you can create other things. You get a system with different angular momentum, and then you put a constraint between them, and suddenly you are creating something weirdly shaped. So that's where I would look for weird situations. But I have no idea.
Okay, talking about donuts so much, I need to get breakfast. So I'm gonna leave.
Exactly. Okay, so we close it here. Thank you for everybody for staying, and thank you everybody who is watching us on YouTube. And see you next time.
Bye.
Thank
Have a nice
you.
week.
Bye.
Bye.